Hello guys, in this video I'll be talking about IR spectroscopy. This is the new playlist that is going to be added in my YouTube channel, and I'll be following the Introduction to Spectroscopy book written by Pavia and co-authors, and in this playlist I'll add videos about infrared spectroscopy. Like in this video we will be discussing the introduction of IR spectroscopy, regions, different regions, functional group region and fingerprint region, what are the main purposes of IR spectroscopy, or how IR spectroscopy helps us to understand the vibrational nature of molecule, what is the principle of IR spectroscopy, what is the electromagnetic radiation in spectrum. So these topics will be discussed in this video, but later on in more videos that I'll upload about IR spectroscopy, we will discuss in depth about different functional groups of organic compounds that show IR spectra, and we will be dealing with the IR spectra of polymers and peptides, amino acids, different heterocyclic compounds, so many other things that will be discussed related to IR spectroscopy in this playlist. Okay, and if you see anything blurry image, or if you are unable to follow the text I'm talking about in this video, please drop down the email below in this video, and then I'll send you the book of spectroscopy written by Pavia. Okay, let's move on to the next slide. Alright, so almost any compound having covalent bond, whether organic or inorganic, absorb various frequencies of electromagnetic radiation in the infrared region of the electromagnetic spectrum. So what is electromagnetic spectrum? A spectrum that contains different regions of frequencies or different regions of wavelength, including X-rays, ultraviolet, visible spectroscopy, IR spectroscopy, NMR spectroscopy, and microwave. This region lies at wavelength longer than those associated with the visible light. So the visible light is from 400 to 800 nanometers, and below 400 is UV region. So that is 400 to 800 nanometer corresponds to visible light, and 1 nanometer is equal to 10 power minus 9 meters, but lies at wavelength shorter than those associated with microwaves. So IR is in between visible and microwave, which are longer than 1 millimeter. For chemical purposes, we are interested in the vibrational portion of the infrared region. It includes radiation with wavelengths. So wavelength is indicated or designated by lambda, that is between 2.5 micrometer to 25 micrometer, and 1 micrometer is equal to 10 power minus 6 meters. Although the more technically correct unit for wavelength in the infrared region of the spectrum is micrometer. You will often see the micron used in infrared spectra. Figure 2.1 illustrates the relationship of the infrared region to the others included in the electromagnetic spectrum. Okay, let's first discuss figure 2.1 and then we will come back to this slide. Okay, this is figure 2.1, a portion of the electromagnetic spectrum showing the relationship of the vibrational infrared to other types. So X-rays are the far out in the left hand side, and the nuclear magnetic radiations or radio wave wavelengths are far out on the right hand side. So the next is ultraviolet, and next is visible, then next is infrared or vibrational infrared, and next is microwave, and then next is radio, and then next to radio is NMR. Okay, nuclear magnetic resonance. So X-rays possess the shortest wavelength, and the radio waves possess the highest wavelengths. And keep in mind that the relationship between wavelength and frequency is inverse. They are opposite in relationship. So what does it mean? That if we have a higher wavelength, then we should have a low frequency, and if we have a low wavelength, then we should have a higher frequency. So if you see, the wavelength on the left hand side is short and the frequency on the left hand side is high, and the wavelength is long on the right hand side and the frequency is also low. Moreover, energy and wavelength are also inversely related to each other. So if we have a high energy, the wavelength will be low. If we have a longer wavelength, then energy will be low. You can see energy similar to frequency is high on the left hand side, and energy is low on the right hand side on the electromagnetic spectrum, and wavelength is short on the left hand side and long on the right hand side. Moreover, frequency and energy are directly related to each other. So higher the frequency, higher will be the energy, and vice versa. But frequency and energy both are inversely related wavelengths. Okay, so the ultraviolet region begins from 280 and ends at 400 nanometer, and 400 to 800 nanometer region is called the visible spectrum region, and that starts from blue to red. And then we have a vibrational infrared that starts from 2.5 micrometer to 15 micrometer. And then we have microwaves, then we have radio frequency waves, and then we have NMR resonance that is from 1 meter to 5 meter. And this is wave number nu bar rather than wavelength mu r min. Okay, let's go back to this one where we would say that we have figure 2.1 shows that the wavelength is inversely proportional to the frequency nu and is governed by the relationship nu equals to c divided by lambda, where c is the speed of light. So if you sometimes in the exam you are asked to calculate the frequency, if you are given wavelength you can follow this equation to calculate frequency. Also observe that the energy is directly proportional to frequency, as I mentioned earlier. E is equal to h nu and h is Planck's constant. From the latter equation you can see qualitatively that the highest energy radiation corresponds to the X-ray region of the spectrum, where the energy may be great enough to break bonds in molecules. At the other end of the electromagnetic spectrum, the radio frequencies have very low energies, only enough to cause nuclear or electronic spin transitions within molecules, that is nuclear magnetic resonance NMR or electron spin resonance ESR respectively. Table 2.1 summarizes the regions of the spectrum and the types of energy transitions observed there. Here is the table 2.1. This is table 2.1, types of energy transitions in each region of the electromagnetic spectrum. And this is the region of the spectrum. This is X-rays, ultraviolet, visible, infrared, microwave, radio frequency radiation. So if you apply X-ray radiation, they are able to cause bond breaking because they are shortest in wavelength and highest in energy. Then we have ultraviolet and visible radiation, they are able to cause electronic transitions. Then we have infrared radiation, they are able to cause vibrational transitions. Then we have microwave radiation, they are able to cause rotational transitions. Then we have radio frequencies, nuclear spin, nuclear magnetic resonance, electronic spin, electron spin resonance. So these are the energy transitions that can be caused by either of these radiations. Okay, let's go back to discuss table 2.1. And table 2.1 summarizes the regions of the spectrum and the types of energy transitions that are observed there. Several of these regions, including the infrared, give vital information about the structures of organic molecules. Nuclear magnetic resonance, which occurs in the radio frequency part of the spectrum, is discussed in chapter 3, 4, 5, 6 and 10, whereas ultraviolet and visible spectroscopy are described in chapter 7. I'll be making more videos about in a new playlist related to nuclear magnetic resonance, that is NMR, and I'll be following the notes from the Pavia Introduction to Spectroscopy book, chapter 3, chapter 4, chapter 5, 6 and 10. That will be the new playlist that I'll be adding in my channel very soon. But I have already created a playlist related to ultraviolet and visible spectroscopy, and I'm also following the same book, Introduction to Spectroscopy, and that is the chapter 7, which is related to ultraviolet UV visible spectroscopy. So if you are interested to learn about UV visible spectroscopy, please watch my channel, and the playlist name is ultraviolet UV visible spectroscopy. Okay, but here in this playlist we will be discussing about IR spectroscopy. Okay, let's move on. We already discussed this electromagnetic spectrum, and then we discussed this table 2.1. Now this is the wave number. Wave numbers are expressed as reciprocal centimeters and are easily computed by taking the reciprocal of the wavelength expressed in centimeters convert a wave number to a frequency nu by multiplying it by the speed of light expressed in centimeters per second. Nu bar per centimeter is equals to 1 divided by wavelength centimeter. Nu is hertz, nu bar c divided by wavelength. And then you can convert the units for per centimeter. The main reason for chemists to prefer wave numbers as units is that they are directly proportional to energy. A higher wave number corresponds to a higher energy, and the IR region is from 4000 to 400 per centimeter. This range corresponds to wavelength of 2.5 to 25 micrometer. We will use wave number units exclusively in this textbook, and this textbook is Introduction to Spectroscopy by Pavia and co-authors. You may encounter wavelength. Encounter means experience. Wavelength values in older literature. Convert wavelengths, micron or micrometer, to wave numbers per centimeter by using the following relationship. This equation can be used to convert units. Then we have the infrared absorption process. As with other types of energy absorption, molecules are excited to a higher energy state when they absorb infrared radiation. So as you already know that when molecules are in ground state, they are in low energy, but when molecules absorb any energy, they go into a higher energy level. That's called excited state. Similarly, if the molecule absorbs infrared radiation, that is going to be excited and that is going to have a higher energy state. The absorption of infrared radiation is like other absorption processes, a quantized process. A molecule absorbs only selected frequencies, energies of infrared radiation. The absorption of infrared radiation corresponds to energy changes on the order of 8 to 40 kJ per mole. Radiation in this energy range corresponds to the range encompassing the stretching and bending vibrational frequencies of the bonds in most covalent molecules. In the absorption process, those frequencies of infrared radiation that match the natural vibrational frequencies of the molecule in question are absorbed, and the energy absorbed serves to increase the amplitude of the vibrational motions of the bonds in the molecule. Note, however, that not all bonds in a molecule are capable of absorbing infrared energy, even if the frequency of the radiation exactly matches that of the bond motion. Only those bonds that have a dipole moment that changes as a function of time are capable of absorbing infrared spectroscopy. So the principle of IR spectroscopy is dipole moment. So as molecule absorbs the IR radiation, that radiation causes molecules to vibrate, and that is detected in the IR spectroscopy. And molecules that do not have dipole moment, they are symmetrical, they do not have any separation of charges, they are going to be called IR inactive. And how we can detect IR inactive molecules? There is a technique. There is a new technique that is called Raman spectroscopy, which is quite similar to IR spectroscopy but slightly different from IR spectroscopy. And I will be making a separate playlist about Raman spectroscopy, where I will discuss the principle of Raman spectroscopy and the uses of Raman spectroscopy. But here, in short, what is the principle of IR spectroscopy? That is the dipole moment. So as long as molecules have dipole moment, they are going to be IR active. Okay, it doesn't matter how big or how small dipole moment is, at least they don't have zero dipole moment. If the dipole moment is zero, they are going to be IR inactive. And those molecules which have IR dipole moment zero, they are symmetrical mostly. So of symmetrical bonds such as those of H2 or Cl2, so many others, do not absorb IR radiation, hence they are IR inactive. A bond must present an electrical dipole that is changing at the same frequency as the incoming radiation for energy to be transferred. The changing electrical dipole of the bond can then couple with the sinusoidally changing, I can't pronounce this, electromagnetic field of the incoming radiation. Thus, a symmetric bond that has identical or nearly identical groups on each end will not absorb in the infrared. For the purposes of an organic chemist, the bonds most likely to be affected by this restraint are those of symmetric or pseudo-symmetric alkenes and alkynes. So alkenes are carbon having double bond carbon, and alkynes are having carbon triple bond carbon. So these are the symmetrical molecules that They do not have any dipole moment, hence they are unable to absorb IR radiation, hence they are called IR inactive. Okay, what are the uses of IR spectrum? One, it serves as a fingerprinting technique for detection of organic molecules. Second, it gives the structural insights of the bonds present in a molecule. So since every type of bond has a different natural frequency of vibration, and since two of the same type of bond in two different compounds are in two slightly different environments, no two molecules of different structure have exactly the same infrared absorption pattern or infrared spectrum. Although some of the frequencies absorbed in the two cases might be the same, in no case of two different molecules will their infrared spectra, the patterns of absorption, be identical. Thus, the infrared spectrum can be used for molecules much as a fingerprint can be used for humans. Like every different human being has a different fingerprints, even though two human beings may look similar in their facial expressions or in the body structure, but they are going to have a different fingerprints. Even twins have different fingerprints. By comparing the IR spectra of two substances thought to be identical, you can establish whether they are identical in fact or they are different. If their IR spectra coincide peak for peak, absorption for absorption, in most cases the two substances will be identical. So IR spectroscopy serves as a fingerprinting technique for detection the organic or molecules that possess covalent bond, or they are capable of showing us some sort of dipole moment. Those compounds can be detected or can be characterized using IR spectroscopy, and that IR spectroscopy, the use of IR spectroscopy is serving as a fingerprinting method for detection of different vibrational energies or states present in the covalent bond. Next purpose or second use of IR spectroscopy and more important use of IR spectrum is to determine structural information about a molecule. As any molecule could possess NH bond, CH bond, OH bond, CX bond, or carbonyl compounds, or double bond, triple bond with nitrogen. So different bonds can be present in single molecule, and each bond could be characterized, could be identified using IR spectroscopy, because every single bond is going to have a different IR radiation spectrum. Like NH, CH appear in the different region, carbonyls appear in different, and carbon triple bond carbon appear at different, and the carbon double bond carbon appear at different region. Okay, a small range of absorption can be defined for each type of bond. Outside this range, absorptions are normally due to some other type of bond. For instance, any absorption in the range 3000 plus or minus 150% is almost always due to the presence of a CH bond in the molecule. And absorption in the range from 1715 plus or minus 100 is normally due to carbon double bond. So what I mean by this is that if you see a peak around 3000 plus minus 150 per centimeter, means either 3150 or less than 3000, slightly less than, that is about 150%, that could be due to carbon single bond hydrogen. And the peak at 1715 or plus minus 100, it could be 1615 or 1650 or 1680 or 1700, that could be attributed with carbon double bond oxygen, that is called carbonyl group, which is commonly present in aldehyde, ketone, carboxylic acids and its derivatives such as esters, amides, acid chlorides and anhydrides. The same type of range applies to each type of bond. Figure 2.2 illustrates schematically how these are spread out over the vibrational infrared. Try to fix this general scheme in your mind for future convenience. This is the general scheme. Try to fix this in mind if you can. That will be super easy for you to interpret IR spectrums. Let me give you the guidelines. If you see a peak around 4000 to 2500, it could be either due to OH. Now you should be able to rethink what functional group contain the OH group. It could be carboxylic acid, it could be alcohol, it could be phenol. And what kind of functional group possesses NH bond? It could be peptides, it could be secondary amides, it could be secondary amines, and CH bond is almost present in all organic compounds. So if you see a peak around this region, it could be due to this. But we will discuss in more detail about each single functional group and their characteristics, and we will explain in detail why some groups absorb IR spectroscopy at higher wave number and why some groups absorb IR spectroscopy at lower, and what is the effect of substituents on the IR spectroscopy, like what is the effect of hydrogen bonding on IR spectrum, what is the effect of resonance on IR spectrum, conjugation, say. So we will discuss the factors affecting on the IR spectroscopy later on in the next video maybe, but I'm explaining to you in this video that how you can generalize or how you can use these some simple identification tips to understand the IR spectroscopy. So if you see a triple bond between carbon and carbon or carbon nitrogen or this one, that is due to the if you see a peak around 2000 to 2500, that could be due to triple bond between carbon or triple bond between carbon nitrogen and this one. And if you see this is a very rare, very few bands appear from 2000 to 1800, but if you see a peak around 1800 to 1650, that could be due to carbonyl group. And if you see a peak from 1650 to 1550 in the IR spectrum, that could be due to benzene or carbon double bond nitrogen or carbon double bond carbon, that is alkene. So the question arises, why alkene appear at 1650 and why alkynes appear at 2000? We will explain in more detail in the next videos. Please keep watching this playlist about IR spectroscopy. You will learn a lot. Then this is a single bond region, carbon single bond carbon, carbon single bond nitrogen, carbon single bond oxygen, and alkyl halides, carbon single bond chlorine, bromine, iodine, fluorine. So this is the guideline which you can use to predict which peak could be possibly due to which bond type. Okay, all these bond types could be present in single molecule. By using IR spectroscopy, you can identify even a single bond, single fragment like OH, CH, NH, triple bond, double bond, benzene ring. Using IR spectroscopy, you can characterize different bonds. Okay, this is the last slide of this video. I'm rephrasing what I stated earlier. IR spectrum is divided into two big massive regions. One region is called functional group region and the other region is called fingerprint region. So functional group region starts from 4000 and goes to 1500, and the fingerprint region goes from 1500 to 500. And the functional group region gives you the idea about single bonds, triple bonds, and double bonds. And the fingerprint region gives you the idea about skeletal vibrations and single bonds. So the OH, NH, CH, they appear in this region, and triple bond between carbon or carbon nitrogen appear in this region. Double bonds appear in this region where the blue lines are, and these purple lines showing the single bond are skeletal vibrations. So fingerprint method, and the IR spectrum is x-axis is the wave number in per centimeter and the y-axis is the absorbance or transmittance, 100% transmittance or absorbance. So this is the IR spectrum and there are main regions. This is the classification, the division. So if you keep this picture of IR spectrum in your mind, you can possibly assign the peaks to the different bonds and interpret the IR spectrum. But in other videos about IR spectroscopy, we will be discussing in more detail about different aspects of IR spectroscopy. Thanks for watching. Take care. Bye.